Hi everybody! So what we're going to do in this video is introduce you to the way that the AP questions are going to pull together all of the topics that we've done so far in this chapter. So the next two questions are two examples of former AP FRQs, one of which we're going to use a calculator and one of which we're not, that really pull together all of the ideas that we've covered so far. So it says here, a tank has a height of 10 feet. The area of the horizontal cross sections of the tank at height h feet is given by the function A. So A is the area of the horizontal cross sections. I'm going to go ahead and label that here. The function A, is both continuous and decreases as h increases. Selected values for A are given in the table above. Use a left Riemann sum with the given three subintervals indicated by the data in the table to approximate the volume of the tank. Indicate units of measure. So you might be thinking, how can we approximate a volume when what we have here is the area? One of the things we learned in this unit is that we can use the area of cross sections and just add them up in order to get the volume. We called it volumes by slicing, and we said we could do this when we had the area for each cross section. In this case, they've given us the area of the cross section. So we know that to get the volume, we can use a left Riemann sum. With three subintervals, we're going to use the left side of each subinterval to indicate which side the height's going to be located on. Now in this case, the h is acting like the x values and the area values are acting like the y values. So along the bottom here, my intervals are going to go from 0 to 2, 2 to 5, and 5 to 10. My heights that correspond to the left side would be 50.3, 14.4, and 6.5. So the volume could be approximated by the integral from 0 to 10 of my area formula, which, if I actually do these calculations, would be 2 times 50.3 plus 3 times 14.4 plus 5 times 6.5. Now, this is a calculator question. So at this point, I would just take out my calculator and I would type everything in. 2 times 50.3 plus 3 times 14.4 plus 5 times 6.5. And I would get 176.3. Now it does specifically say in the question to indicate the units of measure. The units here are going to be volume units. So square feet, if we turn that, we multiply bases times heights, square feet times another feet, would be feet cubed, which makes sense because volume units are usually units cubed. In part B, it says, does the approximation in part A overestimate or underestimate the volume of the tank? As soon as I'm asked whether a Riemann approximation is an overestimate or an underestimate, I know that I need to look at the shape of the graph. If I go back to the original instructions, it says the function A is continuous and decreases. So I'm going to picture a graph that is decreasing. Now, if this graph is decreasing and I use the left side to make the heights of my rectangles, what I can do here is visualize that all of those rectangles would be too large. So I would say that the estimate in part A is an overestimate because of a combination of two things. Because A of h decreases And because a left Riemann sum was used. Now it's really important here that we state both the fact that the function was decreasing and a left Riemann sum was used, because if we had a decreasing function but we had used a right Riemann sum, it wouldn't have been an overestimate. So you need to say both of those things in your justification for why the answer is an overestimate. Part C says the area in square feet of the horizontal cross section is modeled by the function f. So, in other words, this is one way that we modeled the area in square feet. Here's an equation instead of a table of values that gives us the same information, the horizontal cross section. Based on this model, find the volume. Anytime I have a cross section and I want to find a volume, I know that I need to integrate the area formula. So my volume here would be the integral from, it says that the tank has a height of 10 feet, from 0 to 10. That's how I know to make my interval go from 0 to 10, because my height is going to go from 0 to 10. But this time, instead of integrating my area values from the table, I'm going to integrate this function, because this is another formula for that area. Now you'll notice I'm saying dh here because the variable that we're given here is an h. I'm going to go ahead and type this in, because again, this is a calculator question. 0 to 10 of, here we go, 50.3 over e to the 0.2 plus x, 0.2x plus x, which gives us 101.325. And the units, because it does specifically say here to indicate the units, would be feet cubed. Now before we move on to the last part, I just want to make sure that you take a second and make sure your work makes sense. In part A, we estimated the volume was about 176. In part B, we said this was an overestimate. It was too big. And in part C, we got the exact volume was only 101. These three parts of the question all go together. They all make sense together because this number is bigger than this number, which is what we said we expected based on our data. Finally, in part C, it says water is being pumped into the tank. When the height of the water is 5 feet, the height is increasing at a rate of 0.26 foot per minute. So the height is 5 feet. They're giving me an h value. And the height is increasing at this rate. So they're giving me how fast the height is changing. So I like to call that dH/dt. I'm just going to try to make sure I know what I have in this question. Using the model from part C, find the rate at which the volume of the water, so rate at which the volume of the water is changing with respect to time when the height is 5 feet. As soon as I see that I've got a rate here and I'm trying to figure out another rate here, it tells me that this is a related rates question because we have rates that are related to each other. The first thing I'm going to do is set up a formula for the volume, because if I want the rate at which the volume is changing, I need a formula for the volume so that I can take the derivative. Now we actually set up a formula for the volume here. The volume of the tank is always going to be the integral of my f function. But what am I going to integrate to? Although I want to know how fast the height of the water is changing at 5, I need to set up a general equation here. So I'm not going to use the number 5 in this setup. For any height that I wanted, here I went all the way to the top of the tank, 0 to 10. But for any height I wanted, I would just integrate from 0 to whatever that height is of my area function. Now you'll notice this also has an h. I'm going to go ahead and change that to an x because I can't use the same variable here and here. So any volume I want is going to be the integral from 0 to whatever height I decide to stop at of f of x, that same function from part C. Now, it says we want dv over dt, which means I need to take the derivative of this integral. But to take the derivative of an integral, we know we can just drop in the bounds. So this would just be f of h, and then multiply by the chain, the derivative of the bounds, which is dh over dt. Now I can see that I can actually plug in my h, which is 5, and my dh over dt, which they provided me with, is 0.26. So dv over dt evaluated when h equals 5 would be f of 5 times 0.26, and now I'm just going to go ahead and use my calculator. So I would plug in 5 to here, 50.3 over e to the 0.2 times 5 plus 5 times 0.26. I get 1.694. Now, what would my units of measure be? Well, what I just found was dv over dt. My units of measure then would be the rate of change of the volume. So feet cubed per, and it says we're using per minute here, so I would use per minute. All right, this is one FRQ example. Now let's look at a non-calculator example. So it says in this problem, let R be the region bounded by the x-axis and the graph of y equals the square root of x and the line x equals 4. Part A says find the area of region R. So I'm going to go ahead and sketch a graph because I know when I'm trying to find my area, that's really helpful. My square root function is going to look like this. And x equals 4 is going to be a vertical line here. I want to find the area of this region. To get the area of this region, I would just do the integral from 0 to 4 of top minus bottom, which is what we learned originally in this chapter. So I would have square root of x minus 0 dx. Now this is a no calculator question, so in order to actually compute this integral, I would think of the square root of x as x to the 1/2. So I would have to do the antiderivative, which would be x to the 3/2, and then I would have to divide by 3/2, which makes 2/3 from 0 to 4. I would plug in my 4 first, so 2/3 times the square root. I'm going to do 3/2 in two parts. I'm going to do the square root first. So the square root of 4, which is 2, then cube that, which is 8. Minus, now when I plug in 0, I just get c. The c's cancel, and I should get 16/3. Part B says the vertical line x equals h divides R, this guy, into two regions with equal areas. Write, but do not solve, an equation involving integral expressions whose solution gives the value h. So I know that my goal here, based on this question, is to write an equation. There better be an equal sign that has integrals in it, where h is one of the variables. So let's try to visualize what's happening here. What they're saying is you're going to take this region that you just found the area of, and you're going to draw a vertical line somewhere between the 0 and the 4. Right? So this is the beginning is 0 and the end is 4. We don't know where to draw the line, but we want to draw it in a place where this region has two equal areas now. The left side has an area that is the same size as the right side's area. So in order to figure this out, we need to set up an equation that shows us that those two areas would be equal. So the area on the left side would be the integral from 0 to wherever h is. My left side area stops at this vertical line, so I would put h here. And then I would do top minus bottom, which is the square root of x dx. Now we want this left side area to be equal to the area on the right side, the orange area. So the orange area would start from h and end at 4. It goes from h to 4. And then I would do top minus bottom, which is square root of x dx. Now we don't have to actually solve this, but if we did solve this, if we could figure out how to solve this equation, what makes this integral equal to this integral, we would have the value of h so that we could make two equal areas. Part C says, find the volume of the solid generated when r is revolved around the x-axis. So again, same region. We're going to revolve it around the x-axis. So the bottom half of my region would be down here. Now because there's no gap in the middle, I know that I don't have to use washers, like there's a hole in the middle, but I do need to use my volume formula for cylinders. Volume is pi r squared h. In this case, my r would be the distance from the top to the bottom, which would be the square root of x minus 0, which is just the square root of x. And h would be dx, because all of my heights of my cylinders would be very tiny chunks of x. So my volume would be the integral from 0 to 4 of pi times r, which is the square root of x squared dx. Now, if I have to do this by hand, my first step is going to be to factor out the pi. I'll deal with the pi at the end. And then I'm also going to do a little simplifying because a squared and a square root cancel. I know I need to do an antiderivative in order to evaluate an integral. So the antiderivative of x would just be 1/2 x squared plus c, and we're going to evaluate that between 0 and 4. If I plug in the number 4, I get 16 divided by 2, which is 8 plus c. And if I plug in the 0, I just get c. So the c's cancel, and I get 8 pi. Finally, in part D, the vertical line x equals k, so there's a new vertical line, divides region R into two regions so that when those two regions are revolved around the x-axis, we get equal volumes. Write but do not solve an equation involving integral expressions, so there should be integrals in there, that give the value of k. Now this is a very similar question to what we did in part B, only instead of creating a shape that has two separate areas that are equal, we're taking this three-dimensional shape that we created in part C, and we're dividing it up and so it has two separate volumes that are equal. So if I were to sketch a picture of this, I want to know, where can I draw this line so that the volume on the left is equal to the volume on the right. So let's set up the volume on the left. The volume on the left would be the integral from 0 to wherever k is, and we would have pi times the radius, which in this case is top minus bottom, so square root of x squared dx, we want that to be equal to the integral from starting from k now until the end, which is 4, pi times the top minus bottom, which is the square root of x squared dx. So this is the left volume, and this is the right volume. All right, that kind of gives you a good sample of some of the types of AP questions that are going to come up when you take the AP test. We're going to do a bunch of practice when I see you in class, so thank you so much for watching and have a great afternoon.